A very good morning to one and all. I am Dr. Meenashy, Senior Resident from the Department of Anesthesiology. And today's class is about modern vaporizers. In the previous class, we've learned about the physical laws governing the vaporizers. And I told you physics is important because inhalational agents vary a lot in their physical properties. We've read about saturated vapor pressure and critical temperature, boiling point, and specific density. So we know that each and every inhalational agent varies in their own physical properties. Therefore, the vaporizer should also vary since every vaporizer is agent specific. And keeping in mind about the physical properties, we've engineered these vaporizers. And now we'll see how each and everything works. Contents of this class. A quick recap of the previous class. Then we'll know about the classification of vaporizers and the method of classification. Thermocompensation in depth we'll detail. And Tech 5, Tech 6, Tech 7 vaporizers, dragger vaporizers, modern vaporizers like Aladdin Cassette, Diva, and Anaconda. And also we'll be describing about the safety features of vaporizers. Okay, so what is a vaporizer? Like we already discussed in the previous class, vaporizer is an instrument or a delivery device that is designed to facilitate the change of liquid anesthetic agent into its vapor and add a controlled amount of this vapor into the fresh gas flow or the breathing system. So we know that it's an instrument, it's an equipment. We fill it with liquid anesthetic agent. Liquid anesthetic agent that comes in amber colored bottles you've seen in the OT. So we'll fill this liquid anesthetic agent into the vaporizer, and the vaporizer will turn this liquid into a vapor, that is a gas, and it will add it in a controlled manner into the fresh gas flow. That controlled manner, we'll set the concentration, we'll set the dial, and according to that, this vapor will be added in a controlled manner into the fresh gas flow, and it will help in the maintenance of anesthesia. Okay, this is classification of the vaporizer. According to the pressure of fresh gas flow needed, it is divided into draw over and plenum vaporizer. Draw over is fresh gas flow at atmospheric pressure is drawn through the vaporizer. So the surrounding atmospheric pressure is facilitating the fresh gas flow. In plenum vaporizer, the pressurized fresh gas flow is needed for the flow through the vaporizer. So in draw over, the fresh gas flow is sucked up and drawn into the vaporizer. And in plenum vaporizer, we are pressurizing the fresh gas flow to flow through this vaporizer. All our modern vaporizers are plenum vaporizers. Okay, for draw over vaporizers, the examples are Goldman and EMO vaporizer and Oxford Macintosh vaporizer. All these are very old vaporizers. In plenum vaporizers, we can see Tech series, Drag or Aladdin Cassette. That's what we use today. And second classification is according to the method of vaporization. Method of vaporization could be anything. Can be flow over without wicks or with wicks. Flow over as in the fresh gas flow. The gas will flow over the vaporizing chamber. And bubble through. In bubble through, the gas is being bubbled on the surface of contact for the liquid anesthetic agent. It can be flow over or bubble through, or it can be injection type. In injection type, we will set some amount of concentration that is carefully being injected into the fresh gas flow. So the fresh gas flow doesn't go inside the vaporizer or flows through or bubble through. Just it is separately being injected into the fresh gas flow. So for examples, flow over without wicks, we have Goldman vaporizer. Flow over with wicks, we have Rombotham and EMO and Oxford Macintosh vaporizer. For bubble through, we have copper kettle and Vernitol. And for flow over or bubble through, we have Boyle's bottle. For injection type, we have Siemens Kion and Anaconda device. Anaconda is again a modern vaporizer. And we can classify them according to the method of regulating vaporizer output. Regulating vaporizer output, it can be variable bypass or measured flow. We've talked about variable bypass in the previous class, where we have a vaporizing chamber, we have a bypass chamber, and a splitting ratio is fixed. For example, variable bypass vaporizers are Tech 4, 5, and 7, and Dragger Vapor 2019. For measured flow, we have Copper Kettle and Dragger Diva. Temperature compensation, we've read why temperature compensation is required and the methods of temperature compensation. Temperature compensated, when they use a thermostat, it becomes one type. It can be also non-temperature compensated, thermo-buffered or electrically monitored and regulated. When they're using a thermostat, the examples are Tech 4, Tech 5, Tech 6, 7 and the Draeger 19.1 and 2000. Non-temperature compensated types are Goldman and Siemens Kion. Thermo-buffered is EMO. Electronically monitored and regulated are Tech 6 and Aladdin cassette. And agent specificity. Multi-agent specific are the old ones, Goldman, OMV, EMO, and Boyle's bottle. Agent specific, all our modern vaporizers in use are agent specific. So all the Tech series, the desflurane vaporizers, everything is agent specific. Also, you can classify the vaporizer according to their location in the circuit. It can be vaporizer in circuit, VIC, or vaporizer outside circuit, VOC. So vaporizer in circuit is Goldman and Anaconda, and vaporizer outside circuit is all the plenum vaporizers. Okay, so when you start writing about every vaporizer, first of all, you need to write these 1, 2, 3, 4, 5, 6 points. So these 6 points should be there when you start writing about your vaporizer. You have to classify them according to the fresh gas flow. According to fresh gas flow, either draw over or plenum. According to the method of vaporization, either flow through, bubble through, or injection type. According to your regulating vaporizing output, either variable bypass or measured flow. Then according to temperature compensated, either it is temperature compensated or not. If it's temperature compensated, it is according to thermostat or electrically compensated. Then if it's agent specific or not, then it's inside circuit or outside circuit. So you have 6 points starting here. Each and every vaporizer, you can classify them according to the 6 points. Okay, concentration calibration, that we know because when we see a vaporizer, that is the first thing we see, the concentration dial. Vaporizers are calibrated by agent concentration expressed in percentage of vapor output. We have seen this in the previous class. Concentration calibrated vaporizers, direct reading, dial control, autonomic plenum, percentage type, Tech type vaporizer, it will vary. Dial control is the usual common thing that we see in our OTs in our hospital. There are also percentage type where you can enter the percentage. Okay, starting with variable bypass vaporizers. Variable bypass vaporizers are called like that because they have a bypass chamber, they have a vaporizing chambers. The amount of fresh gas entering these two chambers is variable. That is according to the splitting ratio. Clinically useful concentration is accomplished by splitting the gas that flows through the vaporizer. Like I told you, fresh gas flow enters the vaporizer. A majority of the fresh gas flow will go to the bypass chamber. It will not come into contact with your inhalational agent. Some of your fresh gas flow will go into the vaporizing chamber. There they will be in contact with the liquid anesthetic agent. They will get saturated with the agent. These vapors, when fresh gas flow gets in contact with your liquid anesthetic agent, it forms vapors. So now your fresh gas flow is saturated with your agent and it comes out. And now the air in the bypass chamber, the fresh gas flow in the bypass chamber and the fresh gas flow in the vaporizing chamber, they combine and they are being delivered to the patient. So it's the same. The part flows through the vaporizing chamber and the remainder flows through the bypass chamber to the vaporizer outlet. Both these gas will join downstream to the vaporizing chamber and the gas exits will be in the desired concentration. So you set the concentration that will decide the splitting ratio, that will decide how much fresh gas flow will go inside the vaporizing chamber and how much fresh gas flow will go inside the bypass chamber. As you can see here, fresh gas flow is coming. It is being split, some to the bypass flow, some to the vaporizing flow. Bypass flow, nothing has changed. It is just entering and exiting the same way. In the vaporizing chamber, it will carry some of the vapors. The circular molecules are the agent molecules that get mixed, and in the outflow part, both gas from the bypass and the vaporizing chamber is being mixed. Okay, so I told you your concentration dial will decide the splitting. If you increase the concentration, it will open up less. it will limit the gas that is going inside the bypass chamber, so that a lot of gas will go inside the vaporizing chamber. If you decrease the concentration, that is, if you decrease the concentration, it will come out. The concentration dial will come out, and a lot of it will be pressed inside the bypass. It will be opening up the bypass chamber, so that a lot of gas will go through the bypass chamber. So when you increase it, the dial will come down, so that less number of air molecules will go to the bypass and more will go to the vaporizing chamber. When you decrease the concentration, this dial will go up. So this pathway is open. Lot of fresh gas flow will go by the bypass chamber and very less will go into the vaporizing chamber. Thereby you can decide however you will get your concentration. In most of the types, the concentration dial is either up or in front, and this is the filler cap. That's how you fill your liquid anesthetic agent that comes in a bottle. You have to fill it with a filler or a direct nozzle. That depends upon the vaporizer also. Okay, then there is electronic vaporizer. There are two types of electronic vaporizers. A computer calculates the carrier gas that needs to flow through the vaporizing chamber to produce a desired concentration of anesthetic agent. So we will set the concentration that is required. The computer will calculate how much fresh gas flow needs to go to the vaporizing chamber to produce a desired concentration of anesthetic agent. Withdraws a calculated amount of liquid agent and injects into the breathing system. This is one type. One type, the computer will decide how much fresh gas flow needs to go inside the vaporizing chamber in order to produce the set concentration of inhalation agent. That is one type. In the second type, the computer will inject a known amount of, it will calculate an amount, it will inject this amount into the fresh gas flow just so that you get the desired concentration. Then next is your flow over vaporizer. That is the most common pathway. In flow over vaporizer, like a stream of gas will pass through the surface of the liquids. These fresh gas flow will take some molecules of the inhalational agent and will get saturated with the inhalation agent. In order to increase the surface area of contact, we use wicks or spirals, also called baffles. Most commonly used type is flow over. Efficiency of vaporization is enhanced by increasing the area of the carrier gas liquid interface. Like I told you, we have to create more space for the carrier gas to get in contact with the liquid agent. By using baffles or spiral tracks to lengthen the pathway of gas over the liquid, or using wicks that have bases in the liquid moves up in the wick. By capillary action, it will get absorbed with the agent. So these are wicks. These are nothing but a spiral coil sort of thing. This is baffle. Baffle, in order to stop the straight pathway of the fresh gas, if you keep some interruptions or hindrance here and there, the fresh gas flow will be convoluted. It will come like this. It will move like this. So in order to stop the straight pathway of the fresh gas flow. These are wicks. Wicks are coated with your liquid anesthetic agent. So your fresh gas flow will flow like this, thereby increasing the surface area of contact. In injection type, the vapor concentration is controlled by injecting a known amount of an anesthetic agent from the reservoir in the vaporizer or a bottle of agent into the volume of gas. In injection type, your fresh gas flow doesn't flow over the vaporizing chamber. A calculated amount of the agent is being injected into the fresh gas flow. So fresh gas flow is separate, your vaporizer is separate. Only a amount of vaporizing agent will be injected into the fresh gas flow. That is a calculated amount that will be calculated by the computer according to your set concentration. Okay, then we need to know about thermocompensation. As we know, while vaporization happens, vaporization is the conversion of liquid to vapor. When vaporization happens, it is a change of one matter form to another matter form. So it needs some sort of energy for that to happen. So some calories are lost. Energy in the form of heat is lost when the liquid is being vaporized. The liquid temperature falls, that is your liquid anesthetic agent temperature falls. This results in fall in saturated vapor pressure. If temperature keeps falling, your saturated vapor pressure keeps falling, at one point of time vaporization will stop. But we don't want that. If vaporization stops, it will decrease your vaporizing output. We have to maintain the output in a stable manner. That's why when energy is being lost, we have to compensate for that energy so that vaporization keeps happening and the output's being stable. So several methods have been employed to maintain constant vapor output with fluctuation in the liquid anesthetic agent. Okay, first we'll start with mechanical compensation. Mechanical compensation, this is by altering the splitting ratio according to the temperature changes. A percentage of carrier gas that is directed through the vaporizing chamber is increased or decreased. When there is a fall in temperature, what happens? When there is a fall in temperature, what happens to the vaporization? Okay, right, it decreases. With fall in temperature, vaporization decreases. So the thermal element will restrict the amount of fresh gas flow entering the bypass. It will bypass chamber. It will increase the fresh gas flow that is entering the vaporizing chamber. So more with fall in temperature, the thermal element restricts the flow through the bypass chamber and more carrier gas passes through the vaporizing chamber. The opposite occurs when temperature increases. So when temperature increases, the thermal element will restrict the gas through the vaporizing chamber, right? Then it will increase the gas through the bypass chamber. Okay, right. Okay, we can make this thermal mechanical thermocompensation by two types, bimetallic strip and bimetallic alloy rod. Okay, in bimetallic strip, two dissimilar metals or alloys are placed back to back. These two metals have different rate of expansion and contraction with temperature. So this device has the ability to bend. They have two different coefficient of expansion. Used to vary the degree of occlusion in the aperture of the gas channel alters the flow of carrier gas. So this is your bimetallic strip. The blue is metal A and yellow is metal B. Both two have separate coefficient of expansion. When temperature increases, again this is your bypass chamber. This is your vaporizing chamber. When temperature increases, what will happen? We need more gas in the bypass flow and we need less gas in the vaporizing flow. So when temperature increases, it will expand in such a way that the bypass flow is increased and this is open. So a lot of gas will be going through the bypass chamber and very less gas will be going through the vaporizing chamber. When the temperature is low, in a cooler temperature, it will contract and this will close the aperture so that the flow through the bypass chamber is restricted and more flow is going through the vaporizing chamber. Okay, that is one type, bimetallic strip. In bimetallic device, a central rod is made of invar, a non-expansile metal alloy, sitting inside a brass jacket with a higher coefficient of expansion. So there is an outer brass jacket and the inner rod is made of invar. Invar doesn't expand, only the outer brass jacket will expand with heat. The top part is attached to the roof of the vaporizing chamber. The rod is attached only at the base of the brass jacket. So it means brass jacket is fixed. So the invar is movable. The outer surface of the jacket is immersed in the liquid anesthetic agent in the vaporizing chamber. When the liquid cools, what happens? Brass chamber contracts more than invar and invar is pushed upward into the bypass, restricting the flow of gas. As we know, when the liquid cools, what do we want? We don't want more gas in the bypass chamber. We want more gas in the vaporizing chamber. This is the bimetallic arrangement. Like you can see, the brass jacket, outside brass jacket is immersed into the liquid anesthetic agent. Okay, now the gas goes. This is a higher temperature. In higher temperature, we need more gas in the bypass chamber. We need less gas in the vaporizing chamber. It will expand and the invar rod will come down. When it comes down, you can see the bypass chamber is free. A lot of gas can go through bypass chamber. A very less gas will come to the vaporizing chamber. In a cooler temperature, what will happen? This will contract. It will push the invar rod into the bypass route. So bypass route has a constriction now, has a distraction. A lot of gas cannot go through the bypass chamber. less gas will go to the bypass chamber and more gas will go through the vaporizing chamber, thereby increasing the vaporization. This is what happens in cooler temperature. Always remember, in warm temperature, we need more gas through the bypass chamber. In cooler temperature, we need more gas through the vaporizing chamber. Okay, we have seen about mechanical thermocompensation. There is another type of thermocompensation where we have to supply heat from outside. An electrical heater that can be used to supply heat to the vaporizer and maintain it as a desired constant temperature. Supplied heat we usually see in dust fluorine vaporizers. And computerized thermocompensation, where the thermocompensation is achieved by the computer control. Okay. Until now, we've seen all the classification of vaporizers, all the methods to thermocompensate the vaporizer. Now we are going to see about each and every type of vaporizer, starting from Tech 5 vaporizers. Okay, here, like I told you, you can write 6 points only in the classification of vaporizers itself. So when you talk about a vaporizer, first 6 points should be according to the classification. Okay. Starting with vaporizing methods. What are the vaporizing methods I told you about? Keep talking. Flow over, bubble through, flow over with wicks and without wicks, bubble through, and injection type. So Tech 5 vaporizer is flow over with wicks. Regulation of output can be variable bypass. Variable bypass, it means it has a bypass chamber and a vaporizing chamber. Okay. Concentration calibrated. And temperature compensated. Yes, it is temperature compensated. Automatic thermocompensation, thermostat using a bimetallic strip. So this Tech 5, Tech stands for temperature compensated. That's why it's called Tech. Is it agent specific? Yes, it's agent specific. Is it plenum or drawer? Like I told you, all our modern vaporizers are plenum vaporizers. Location, outside circuit. Yeah, you have seen it only outside the breathing circuit. You have seen it on the anesthesia workstation. It's not inside the circuit, it's outside the circuit. So 6 points of Tech 5, flow over with wicks, variable bypass, concentration calibrated. It is automatic thermocompensated using a bimetallic strip. It is agent specific, it is a plenum vaporizer, it is a vaporizer outside circuit. So if you can see the model of this vaporizer, this is for fixing. This is the concentration dial. And this is your filler. In order to open the filler, you have to keep the lever down. And it will you can fix the filler and fill it up. So what happened is in this type, with one hand you need to open the lever, and with one hand you need to open the concentration calibration, this calibration dial. So you actually need two hands to start it to work. So that was a big disadvantage. As you can see, the vaporizers we use in our OT, with one hand you can press the button and you can turn the concentration dial. Here with one hand you should open this lever down, you should push it down, and only then this vaporizing chamber will open, and with one hand you have to open the concentration caliber. It's here. So control dial is at the top. This is your control dial. It comes with some markings. Release button is located at the rear of the dial here. At the rear is a locking lever here. In the right bottom, there is a slide glass. Here, there you can see the level of inhalational agent that is being filled. Okay, this is a cut surface of this vaporizer. Here you can see how the fresh gas flow enters and leaves. Okay, your fresh gas flow enters like this. So this fully is your bypass chamber. Yeah, it doesn't comes in contact with your vaporizing agent, your anesthetic agent. This is your vaporizing chamber. Here this 4 is your vaporizing your inhalational agent. Okay, so fresh gas flow can come into bypass chamber or go inside the vaporizing chamber. In the vaporizing chamber, this is how you elongate the passage in order to increase the surface area of contact. Okay. and this 3 is the helical wick. Like I told you, helical wicks are spiral components, so that it will take your fresh gas flow in a spiral manner, not in a straight manner, in a spiral manner, thereby increasing the time of contact and increasing the surface area of contact. So it will get saturated. It will come to the base of the vaporizing chamber, and like this, it will come outside. Here, it will join with the gas in the bypass chamber, and this is the outlet. That's how you get a mixture of your bypass and vaporizing chamber. So 5 is your concentration dial. Concentration dial will decide about your bimetallic strip. So this is your bimetallic strip. It will decide how much gas goes into the bypass chamber and how much gas goes into the vaporizing chamber. Okay. Once more. 1 inlet. 2 is your elongated passage. 3 is your helical wicks. 4 is the base of your vaporizing chamber filled with your inhalational agent, liquid inhalational agent. 5 is your concentration dial. 6 is your mixing chamber, where what happens? Bypass and vaporizing chamber gases mix. 7 is your bypass chamber. 8 is your bimetallic strip, that is your temperature compensating device. 9 is your outlet. So this is Tech 5 vaporizer. Okay. When the vaporizer is off, the rotatory valve is closed. The gases will pass through the inlet into one channel, that is your bypass channel. It will not pass through the vaporizing channel. From here, the gases pass through the top of vaporizer without being in contact with your vaporizing chamber and come outside the outlet. So it will just go straight through the top and will come out. That's all. It will never go inside and get in contact with your inhalational agent. When it is open, when you switch on your vaporizer, when it's open, the pathway opens and 2 channels will open. These 2 channels are your bypass chamber and your vaporizing chamber. In your vaporizing channel, the elongated passage that funnels the carrier gas into the center of the wick assembly. It's a hollow tube of Teflon cloth is held open by a steel wire spiral that is wound into a helix. The lowest helix is in contact with the liquid agent, that is the base of your vaporizing chamber. This arrangement will greatly increase the surface area of for vaporization over the previous tech models. The gas passing through the wicks will become more saturated with the vapor and enters a rotatory valve assembly, that is your calibrated control knob. So your control knob decides whether the gas will go inside the vaporizing chamber or not. If it is closed, it will just go straight over the top of vaporizer. It will never come in contact with the liquid anesthetic agent. If it is open, 2 channels will get open, bypass and vaporizer. You know how it happens, and the mixture leaves open. Okay, this is how you fill your agent in Tech 5 vaporizers. I'm sure you would have seen this in ROT. So yeah, this is the amber colored bottle. Amber colored bottle because this liquid anesthetic agent should not come into contact with the sunlight. You will be dealt more about the properties in inhalational agent classes. So this is an amber colored bottle. So this is here is isoflurane. Purple is for isoflurane. The filler comes separately. The bottle comes separately. So if you lose your filler, you will not be able to fill the vaporizer with your agent. So this filler has this bottle has some projections that will fill in the gap of the fillers. So you cannot keep a isoflurane filler into a sevoflurane bottle, and you cannot keep a halothane filler into a sevoflurane bottle, because all these will be different and it won't get fixed. So initially, to do that, you have to get a filler and fix the filler into the bottle, into the top of the bottle, and filler in the end has a key. This key will match with only that vaporizer. Isoflurane filler tube will have a defect here. That defect will be filled in the vaporizing inlet of the isoflurane vaporizer only. It will not get fixed with the halothane or sevoflurane vaporizer. Like you can see here, halothane vaporizer has a projection on this wall, and isoflurane vaporizer has a projection in the corner of this wall. So Your filler has to fix with your inlet. Only then you can fix. All these are safety systems. Your color coding is a safety system. Isoflurane is purple. Halothane is red. Which color is sevoflurane? Yellow. Correct. So that color coding is a safety feature. Your filler tubes will not match with your bottles if it's of a different agent. The projection should match with the deficit in the cap. So that is again a safety form. And your key has a deficit that should be filled in the vaporizing inlet. You cannot keep a halothane filler fixed into a isoflurane vaporizer. That is again a safety system. But the down point in this system is if you lose your filler, you will not be able to fill the vaporizer. You can have your you can keep your bottle full of agent, but if you lose your filler cap, what will happen? You cannot fill it in the vaporizer. So that has to be kept separately and safely. So here, the locking lever, you have to unlock the lever. You have to fix this filler tube into the draining port. Then you have to raise the bottle. And when you unlock it, you can see it filling up in the slide glass. Slide glass is to see how much agent is left. You have to fill it or you have to take it somewhat less if it's too much. So you have to hold the bottle like this upside down so that via gravity it will get filled. If you want to empty the chamber, if you want to take back the vaporizing agent that is inside the vaporizer, you can keep it down so that via gravity from the vaporizer it will get filled into the bottle. Okay, so you can fill it and you can unfill it. Okay, next is Tech 7 vaporizer. That is the most common vaporizer in our OT. Okay, like I told you, 6 points in every vaporizer. According to vaporization method, this is flow over with wicks. Okay, most common. Regularization of output, this is variable bypass. It has a bypass chamber and it has a vaporizing chamber. It is a temperature compensated. Every tech vaporizer is a temperature compensated vaporizer. Thermostat with the bimetallic strip at the bottom. It is agent specific. Like you can see, you have purple vaporizer for isoflurane. You have a yellow vaporizer for sevoflurane. It is a plenum vaporizer. It is a vaporizer outside circuit. 6 points done. Okay. Your Tech 5 vaporizers, we saw key filling system. This is quick fill system for Tech 7. Here, like I told you, in your key filled system, if you lose your filler, you will not be able to fill the vaporizer. So they came up with the next, in the next generation, the vaporization design was evolved and they came up with a nozzle. This nozzle, what happens? This nozzle, you can fix it directly to your filling port. This is your filling port. This round thing is your filling port. You can open this knob, you can fill the nozzle inside, it will get fixed, and if it gets fixed, it will get filled. So here you don't need to use a key filler. This nozzle comes attached with the bottle so that in key fill system, if you lose your filler, you cannot fill the vaporizer. Here that advantage is that is an advantage. You don't have a key filler only. This nozzle comes attached with the bottle. This is quick fill system for sevoflurane. It's also called as easy fill. Okay, next is Tech 6 vaporizer. Tech 6 vaporizer, as you can see, it is blue in color. It is for desflurane only. I'll tell you why it's for desflurane. Okay, the 6 points. According to vaporization method, it is saturated vapor generator. Regulation of output is injection type. It is not variable bypass. It does not have a bypass chamber. It does not have a vaporizing chamber. What is injection type? A calculated amount of the vapor is being injected into the fresh gas flow. So you have to remember that in Tech 6 vaporizer, the fresh gas flow does not come inside the vaporizer. Calculated amount of the vapor agent is being injected into the fresh gas flow. Okay, temperature compensation, it is supplied heat. Supplied heat as in from your outer surface, you have to fill the heat. You have to supply the heat that is being lost. So you have a thermo filament. It is agent specific, like it is for desflurane only. It is a plenum type of vaporizer. The vaporizer is outside the circuit. Okay. Why does desflurane need a very separate vaporizer that is not like our usual isoflurane, sevoflurane vaporizer? It has a very high saturated vapor pressure. Saturated vapor pressure, what is saturated vapor pressure? Pressure at which 50% it's liquid, 50% it is vapor. It is 664 millimeter of mercury at 20 centigrade. So what is 20 centigrade? It is below our room temperature. The number of vapor molecules at equilibrium will be much higher in the room temperature only. So there is a lot of vapor molecules. There is a lot of vapor molecules, but you don't need so much for your anesthesia maintenance. So in order to dilute this, we need to have a lot of fresh gas flow in order to dilute it into a clinically useful concentration. The thing is, it is very much saturated, but you don't want that much vapor. In order to have your usual amount of vapor, you need a lot of fresh gas flow to dilute this. Using a lot of fresh gas flow is not very economical. So that's why it has this very separate type of vaporizer. It also has a very low boiling point, that is 23.5 degrees centigrade. So at room temperature, it will be boiling intermittently. If it boils intermittently, what will happen? Temperature increases, vaporization will increase. Temperature decreases, vaporization will decrease. So there will be a fluctuation in the output. You don't want a fluctuation in output. You want your output to be stable. So at room temperature, it intermittently boils, resulting in large fluctuations in agent delivery. When boiling, excessive agent delivery will be there. Later, it will cool down due to large loss of your latent heat of vaporization. So there will be under delivery. When it boils, excessive delivery. When it doesn't boil, the temperature is lost under delivery. So we have a separate vaporizer, Omega Tech 6 vaporizers, to overcome these problems by using an electrical filament that heat the desflurane. So electrical filament that heats the desflurane is the method of supplied heat of thermocompensation. Okay. So first you need to know that this is an injection type of vaporizer. So vaporizer, it doesn't have a vaporizing chamber. It doesn't have a bypass chamber. The fresh gas flow does not enter inside this vaporizer. Fresh gas flow does not enter the vaporizing chamber. Instead, the vapor will enter the path of the fresh gas flow. Okay, the dial calibration is from 1% to 18% on top. It is provided with a backup battery of 9 volt. The front panel has 5 LED lights starting from above. First is operational. That means it indicate that the unit is ready to be used. Actually, we have to switch it on. We have to wait for it to get ready, get heated and get ready, and only then you can use it. So when the operational LED lights blinks only, you can start using that vaporizer. So no output is the next LED. That is when the agent drops below the minimum operating level. That means it's time to fill up. Low agent is before your no output state to indicate that refilling is required. You have to be vigilant. When low agent light blinks only, you need to start filling up. You need not wait until it goes to the no output state. Then there is warm up LED light, and then there is alarm battery low when the backup alarm power is low. So you need to switch on and connect it to a AC power. When operating temperature is reached, the warm-up light will become the warm-up light that is amber in color will go off. Then operational light will become green. It will switch on, and only then the concentration dial can be unlocked. So you need to know that before using a desflurane vaporizer, you have to switch it on. You have to wait for some time, give it some time to get heated, and wait for it to blink green in the operational LED light. Only after it blinks green, you can open up the concentration dial. Until then, you cannot unlock. Okay. So here, your one is this. This is a electrical filament that is responsible for the supplied heat. This is your vaporizing chamber. This will get heated up. 2 is your shut-off valve. If the fresh gas flow and the vaporizing chamber is not matching, this will shut off. Okay. 3 is your reservoir that is filled with your desflurane liquid. 4 is the electronic pressure regulator. Pressure regulator so that it will measure the pressure of fresh gas flow and the desflurane. Okay. 4. 5 is your concentration dial on top of the vaporizer. 6 is your vaporizer outflow. 7 is your fresh gas flow. Fresh gas flow comes like this. Here it is a pressure sensor. So 7 is your fresh gas vaporizer. Here the pressure is being sensed. In this side, the vaporization, your vapor pressure is being sensed. Both this will show in this concentration dial. In this pressure regulator. Okay. The reservoir where the desflurane is being filled has 2 thermostatically controlled electrical heating filament that is responsible for heating the desflurane. It will raise the temperature to 39 degrees Celsius. The saturated vapor pressure is 194 kilopascal, that is 1500 millimeter of mercury. When the vapor is required, the shut-off valve will open. Pure vapor under pressure is allowed to escape from the reservoir. So what will happen when you open the concentration dial? 5 is your concentration dial. You will open it. 2 is your shut-off valve. Shut-off valve will get opened, and from your reservoir, this desflurane will go like this. It passes through an electronic pressure regulator that reduces the pressure to a normally found in plenum vaporizer. It will reduce the pressure according to your fresh gas flow pressure. Then to a variable flow restrictor linked in a calibrated concentration selection dial where it is fed into the carrier gas flow. So a calculated amount of your vapor is being injected into your fresh gas flow. That will depend. This pressure will also depend on your fresh gas flow pressure. This percentage is according to the percentage of your fresh gas flow. The pressure sensor is there to sense both the sides, because if there is a mismatch, the shut-off valve will open automatically. Fresh gas flow has to pass through a narrow constriction so that its pressure, that is when the fresh gas flow faces a constriction, what will happen? The pressure will increase and the flow will increase. With the increasing flow, 2 independent sensors in the pathway will detect the pressure rise. This sensor will detect the pressure of fresh gas flow and the vapor acid. It will instruct the desflurane pressure regulator to increase proportionately the pressure and flow to the selection dial so as to maintain the set vapor concentration. So your fresh gas flow pressure is very important because that decides the vapor pressure also. If the readings from your 2 sensors are not similar, the shut-off valve will close immediately, isolating the vaporizing chamber. No more pressure will be regulated. No more vapor will be regulated. Okay, this is much easier. Flow meter is opened, fresh gas flow goes, fresh gas flow comes like this. It will, at this point, in the point of flow restrictor, what will happen? Flow falls and pressure increases. In this time, the pressure is being measured by the differential pressure transducers. This side is your fresh gas flow side, that side is your desflurane vapor side. So if this if there is a mismatch in the pressure, the shut-off valve will close the flow. So it goes through like this and goes like this and goes out. Here in this side, as you know, there is a reservoir. The reservoir is filled with your desflurane, and there is an electrical filament that will heat up the desflurane until 39 degrees Celsius. The SPP is 1300 to 1500. So it goes through a pressure control valve, and then it goes through a desflurane control valve. That is decided according to your vaporizer dial, how much ever you open, how much ever concentration you want. Then it will sense the fresh gas flow pressure. Accordingly, it will increase the flow pressure of your desflurane, and a calculated amount of your vapor will be injected into the fresh gas flow. Here, fresh gas flow and desflurane gets mixed and comes out as a mixture. Okay, what is the filling system for desflurane? It is called safety fill system. This is the port for filling. You can fix the desflurane bottle here, and you can keep it upside down. Only then via gravity it will get filled in the vaporizer. You can also have a side glass here. There is a side glass. You can see the level of the agent there. Okay, next is Drager 19.1 vaporizer. We don't use it much. Again, we'll just see the 6 points. According to vaporizing method, it is flow over with wicks. According to regulation of output, same variable bypass, nothing, not much change in that. And temperature compensation, it is automatic temperature compensation using a metal rod, not bimetallic strip, it is metal rod. Other points are same. It is agent specific. Isoflurane has a separate vaporizer, halothane has a separate vaporizer, sevoflurane has a separate vaporizer. It is plenum type, it is vaporizer outside the circuit. So 6 points are over. Drager vaporizer 2000. Here, vaporizer method is flow over with wicks, variable bypass, automatic thermocompensation, agent specific, plenum vaporizer outside the circuit. Here, the point you have to see here is, can you see a triangle with T on it? So in the previous class, I was telling you about tilting and tipping. What if you're carrying your vaporizer and you bend it slightly? What will happen? The vapor, the inhalational agent that is in the vaporizing agent will spill into the bypass chamber. So next time when you use it, what will happen? The fresh gas flow that goes inside the bypass chamber will also get saturated with your vapor, because there is agent inside your bypass chamber also. So there is something called tilting and tipping, where you're not supposed to tilt your your vaporizer. Drager Vapor 2000 has an option here, where this is your zero dial calibration. Here is your transport. You have to, T is called transport. You have to tilt it so that whenever you are transporting, you're moving the vaporizer. If you keep it in transport mode, the vaporizer chamber will be shut off and there will not be any spill over the bypass chamber. So tilting and tipping will not happen in Drager Vapor 2000. That is a safety feature. Always remember, Aladdin cassette and Drager Vapor 2000 are two vaporizers where there is no spillage or tilting or tipping. When you're transporting it, you have to keep it in the transport mode. That is this small triangle marked T. Okay. In the cut section of the vaporizer, you can see one is your gas input. Your vaporizer, your fresh gas flow comes like this, goes like this. 2 is your damping the chamber. That is just for more elongating the passage of flow. 3 is your tubular wick. Like I told you, tubular wicks are spiral coils that are present to elongate the passage of your fresh gas flow and increase the surface area of contact. 4 is your wick extension. Then 5 is your vaporizing chamber. It is filled with your inhalational agent. Liquid is here. So your gas comes like this, goes like this. According to your, what is this? This is your bimetallic rod. 6 is your concentration control valve. 7, the concentration control dial. What is above that vaporizer? That's how you open it up. The valve will go up and down. When it is closed, what will happen? So when the concentration valve is closed, this concentration, valve will come down. When the dial is closed, the valve will come down so that none of the gas will go inside the vaporizing chamber. When it is open, this will ascend up, it will get open. Some of the gas will go inside the vaporizing chamber. Okay. 8 is your temperature compensation device. This is your bimetallic rod. 9 is your mixing chamber, where vaporizing chamber and the bypass chamber gases mix. 10 is the output. 11 is the bypass tap. 12 is again a bypass tap, where you can close or open it into a vaporizing chamber. So you can see from 1, the gas goes into this. According to this, it can either go into the bypass chamber or it can go into the vaporizing chamber. So for vaporization, it will go via this pathway like this. here, and along with your helical valve, helical wicks, it will get into contact with your inhalation agent. Again, it comes out. The darker blue arrows are saturated with your agent, and it comes out like this. Here the mixing happens and it comes out via the outlet. Everything is similar, just that bimetallic rod is the different thing here. Okay, what is the filling system for a dragger? Comes with a dragger fill system. It is more or less similar to your the easy fill. Comes with a nozzle. Okay, next type is your Penlon Sigma Delta. Here the concentration dial is in front. All these times we saw the concentration dial was on top. Here concentration dial is in front. So follow these arrows. One is your inlet. Fresh gas flow goes like this. 2 is your bypass chamber. Nothing. If the concentration dial is open, what will happen? It will go into the vaporizing chamber. If it's closed, it will go only inside the bypass chamber. It will just come out like this. 3 is your outlet. 4 is your control knob. It will go up and down. Okay. So this is your helical damping coil vaporizing chamber to increase the surface area of contact. 6 is the vaporizing chamber. This gray area is your liquid anesthetic agent. As you can see, light blue becomes dark blue. That is less saturated becomes more saturated. 7 is the wick. Sorry. 8 is your needle valve. When you open it like this, the needle valve goes inside and outside. When it is fully closed, when you don't open the concentration dial, it is closed. Only bypass chamber will work. When you open, the needle valve comes out. Here you can see the bimetallic strip. That is the temperature compensation for this Penlon Sigma Delta. Okay, next is your modern vaporizer, Aladdin cassette vaporizers. Okay, again, according to the 6 components, it is concentration calibrated. It is flow over type with wicks, with helical wicks. It is electronically thermocompensated. So the computer decides the thermocompensation. It can be either used as a measured flow vaporizer or a variable bypass. Variable bypass, what will happen? The fresh gas flow will go inside the vaporizer, go inside the bypass chamber, go inside the vaporizing chamber, and it will act as a normal variable bypass. Measured flow, measured amount of your vapor will be injected into your fresh gas flow. So you have this is your isoflurane. This is the filling filling port. You have a side glass to see the level. This is for yellow for sevoflurane and purple for your isoflurane. You can use key indexed key fill system for this key filling system for filling Aladdin cassette. Okay. Electronically, it controls the gas flow and the vapor concentration. You can actually set the gas flow and you can set the vapor concentration into the computer, and the computer will decide how much gas should flow inside. Agent-specific vaporizer cassette and the central processing unit that is integrated inside the anesthesia machine. Every cassette will have a detachable vaporizing chamber. You can see the black box is the vaporizing chamber. It is a leak-proof metal box which has a smaller front portion which is color-coded to specific agent and a larger rear that is black in color. Black is common for all the agents. These colors are colored and magnetic coded. Your anesthesia machine will actually respond to this magnetic code only. It cannot see which color and all. No? So according to this magnetic code, it will understand whether it is sevoflurane, isoflurane, or desflurane. The signature magnet allows the machine to identify the agent cassette that is being inserted into the machine slot. So there is a slot in your anesthesia machine. That's where you will insert your Aladdin cassette. So this is desflurane, that is blue in color. Okay. You'll see the parts of Aladdin cassette. This is a filler wheel that will lock the key filler. It will open and the liquid channels and gas will get into contact. It is also a protection against overfilling. So you have to open this before you are filling this. So this is your key fill system like we saw in the very first vaporizer. This is a key filling system. This is a liquid level indicator to see if liquid is there or not, or you need to fill where it is time for refilling. This is the agent chamber. This is the eject handle for holding, for storing and inserting. Okay. You can use it as a variable bypass and measured flow. As variable bypass, the bypass chamber has a back pressure regulator that will build up a pressure at the input of vaporizer if necessary to drive the gas through the cassette. So your fresh gas flow will go through the cassette. The detachable cassette, that is that black rear end, will act as a vaporizing chamber. Two separate parts must come together to become a variable bypass vaporizer. As a measured flow vaporizer, the outflow from the cassette, the variable control of flow, is controlled by a proportional valve. That proportional valve is controlled by the CPU. Whatever concentration you enter in the CPU will be decided. The amount of cassette flow is added to the bypass flow to meet the desired concentration of the volatile agent. The desired concentration is whatever the anesthetist sets in the computer. Hence, the control loop of system. Control loop is the anesthesia machine will decide the fresh gas flow, will decide the volatile agent concentration according to whatever set concentration. So control loop of system that depends upon the cassette flow and not the agent concentration which is delivered to the common gas outlet. We will set everything accordingly, it will deliver the gas. The vapor output is not influenced by atmospheric pressure changes. Vapor output concentration is determined by separate environment, that is the total cassette pressure. That is the back pressure that is required to help the flow of fresh gas. The electronic control in the cassette flows for automatic record keeping and usage calculation. Agent control is monitored by a microprocessor up to 200 milliseconds during operation. It cannot function in the presence of power failure when the workstation battery gets depleted because it needs a CPU. Okay, so here one is your VIX, two is a lamellae. Again, both are these for increasing surface contact. 3 is your inlet valve. This blue color thing is the inlet valve. That's how your fresh gas comes in, gets saturated, goes out via your 4 outlet valve. 5 is the contact for electronic temperature sensor and liquid anesthetic level. 6 is the temperature sensor strip. 7 is the ejection handle. 8 is the locking mechanism. 9 is the filling system. 10 is the liquid level window. 11 is agent identification magnet that is not visible, that will be detected by your anesthesia workstation. Okay, Drager DIVA is another modern vaporizer. DIVA stands for direct injection of vapor anesthetic. This is integrated into a ZS anesthesia machine. It allows for target control anesthesia. You just have to enter whatever concentration you need, whatever MAC value you need. Accordingly, the fresh gas flow and the vapor concentration will be decided by the CPU. Closed loop quantitative control of delivery of oxygen, carrier gas, and anesthetic vapor. You just have to enter the desired amount in the CPU. It is an injection vaporizer, measured flow vaporizer, injection vaporizer. So only the calculated amount of vapor will be injected in the path of fresh gas flow. Fresh gas flow will not come inside the vaporizer. Okay, metering or vaporizing module will store the liquid anesthetic agent reservoir with a coded filling system. You can also see a liquid level indicator in front and a ventilation outlet. A gas supply module with a part of anesthesia machine. It consists of propellant gas, that is air, a non-return valve, a pressure buffer, a pressure reducer, a supply valve through which air enters the metering module. So here is it. The liquid anesthetic agent is being filled in the reservoir. You can see the level indicator outside. Liquid anesthetic agent, whatever that is required will come out. Anesthesia dosing chamber is there. Here the liquid becomes vapor. Dosing valve, the vaporizing chamber, vapor, the liquid is being converted into a vapor in a heating chamber. The flow sensor is there. So it becomes an anesthetic vapor. So who decides how much vapor, how much liquid is required to make this much vapor? This is according to your feedback control unit. We will feed the percentage of whatever target we need, that concentration we'll feed it. According to your fresh gas flow, the computer will decide how much liquid it needs, how much vapor to turn into this much vapor, and it will take only that amount of liquid and turn it into a vapor, and this vapor will be injected into the fresh gas flow. Everything depends on target expired agent concentration and fresh gas concentration. Anaconda vaporizer is also called as anesthesia conserving device. Anaconda, that's how the name came. It was designed by Giebel KB and introduced in Stockholm. It is a miniature anesthesia vaporizer combined with a HME filter. It is usually meant for ICU sedation and outside operating rooms. It is designed to deliver only isoflurane and sevoflurane. So this is how it's connected. There is patient's endotracheal tube, and then you connect the anaconda vaporizer, and then you connect the Y piece of the breathing circuit. From the anaconda vaporizer, the one port goes for gas monitoring to show agent levels, and the inlet is via the volatile anesthetic line. The anesthetic agent is being pumped into the vaporizer. So it is a unique oval-shaped device, like you saw. It's a black oval-shaped device. The ventilator inlet and the patient outlet are aligned parallel to the filter. This is to maintain the proper laminar airflow. It will fit in between the Y piece of the breathing circuit and the ET tube like a HME filter. The patient end has an outlet that is directly connected to the ETT or the connector. The patient end has a sampling port that is for end tidal agent concentration. And the vaporizer should always be placed in a 45-degree angle. Okay, this is how it comes in. Anesthetic agent comes in. The liquid becomes vaporized, and it is being sent to the patient. So sevoflurane line is being pumped into the anaconda vaporizer along with HME. The liquid becomes vapor and it is being given to the patient. While coming back from the patient, the whatever sevoflurane that is coming back from the patient via expiration, that is being held up with the active carbon layer. So the sevoflurane that comes back is also stored. That's why it's conserved. Sevoflurane molecules are conserved, and in the next respiration it will go along with that oxygen and air. So that's how it is conserving the vapor molecules. Okay, safety systems in vaporizing agents, there is something called interlock device. Interlock device prevents us from using two vaporizers at a time. So when one vaporizer is open, the other vaporizer cannot be opened. The other vaporizer is locked. This is called interlock device. So when you see this, when you open this vaporizer A, this extension rod will go laterally and push it into the subsequent, the next vaporizer. This will prevent us from opening the next vaporizer. So when this vaporizer is open, the common gas, the fresh gas flow goes into vaporizer A and comes out without going inside vaporizer B. So that's how we use only one vaporizer at a time. Dragger interlock system is another interlock system where when the vaporizer of choice is turned on, a pin is forced into the notch of the control knob of the other vaporizers so that the other vaporizers are closed and cannot be opened until this vaporizer is closed. Other hazards are misfilling, tipping, leaks, overfilling of the agent, no output, or reversal of flow inside the vaporizer. So all these needs to be carefully detected. So how to calculate how much liquid vapor is being used? It's according to Ehrenworth and Ainscraft formula. ml of liquid used per hour is 3 into the fresh gas flow into the dial setting, whatever concentration you are setting. For example, if the dial setting is 2% and the fresh gas flow is 6 liters per minute, ml of liquid used per hour is 3 into 6 into 2. 3 into your fresh gas flow into your dial setting, that is 36 ml per hour. That is how we calculate how much agent we are using up in an hour. These are my references: Watts, Dosh and Dosh, Baheti, and an article about the modern vaporizers. Please do read about them. Thank you and have a nice day.